A standard car engine, known as a naturally aspirated engine, works by sucking air into its cylinders. This air is then mixed with fuel, compressed by a piston, and ignited by a spark plug. The resulting explosion pushes the piston down, turning the crankshaft and ultimately the wheels. The amount of power an engine can produce is directly related to how much air and fuel it can burn in each cycle. To get more power, you need to get more air into the cylinders. This is where forced induction comes into play. It's a method of cramming more air into the engine than it could suck in on its own, allowing it to burn more fuel and generate significantly more power. Forced induction systems are essentially air compressors designed for engines. By force-feeding the engine a denser charge of air, they allow for a much more potent combustion event. Think of it like blowing on a campfire to make the flames bigger. A forced induction system does the same for your engine, but on a much more controlled and powerful scale. This is why a small engine with forced induction can often produce the same amount of power as a much larger, naturally aspirated engine. This has benefits for both performance and in some cases fuel efficiency, as manufacturers can use smaller, lighter engines without sacrificing the power drivers expect. The two most common methods of achieving this are supercharging and turbocharging. Both superchargers and turbochargers are designed to accomplish the same fundamental task: compress air and force it into the engine's intake. However, the way they go about this is fundamentally different, particularly in how they are powered. This core difference in their power source is what defines their unique characteristics, their advantages and their drawbacks. One uses the engine's own rotational power directly, creating a very linear and immediate response. The other recycles energy that would otherwise be lost out of the exhaust pipe, making it a clever and efficient, albeit slightly less direct, method of generating boost. Understanding this distinction is the key to understanding the entire debate. The choice between these two technologies has defined performance cars for decades. Manufacturers and enthusiasts alike weigh the pros and cons based on their specific goals. Are you looking for instant raw acceleration for drag racing? Or are you seeking high-revving power and efficiency for a track day or a daily commute? The answer to these questions will often point you towards one type of forced induction over the other. As we delve into the mechanics of each system, you will see how their operational principles lead to very different driving experiences, each with its own dedicated following in the automotive world. These are not just engineering concepts, they are the heart of what makes many high-performance cars so exhilarating to drive. A supercharger is a type of air compressor that is driven directly by the engine's crankshaft. It is physically connected to the engine via a belt or, less commonly, a gear or chain. This means that as soon as the engine starts spinning, the supercharger starts spinning too. Its rotational speed is directly proportional to the engine's speed, or revolutions per minute. When you press the accelerator pedal, the engine spins faster, which in turn spins the supercharger's internal components faster, forcing a greater volume of compressed air into the engine's cylinders. This direct link is the supercharger's defining characteristic and its greatest advantage. The primary benefit of this direct drive system is the complete absence of lag. Power delivery is instantaneous. From the moment you touch the throttle, even at very low engine speeds, the supercharger is already working to provide boost. This results in a very linear and predictable power curve, feeling much like a larger, more powerful naturally aspirated engine. There is no sudden surge of power. Instead, the thrust builds smoothly and immediately with engine revolutions. This instant response makes supercharged cars feel incredibly potent and responsive, especially when accelerating from a standstill or pulling out of a slow corner. However, this direct connection is also the source of the supercharger's main drawback: parasitic loss. Because the supercharger requires engine power to operate, it effectively steals a portion of the horsepower it helps to create. The engine has to work harder to spin the supercharger, which reduces its overall net efficiency. This means that, for a given amount of boost, a supercharged engine will generally be less fuel efficient than a turbocharged equivalent. The energy used to spin the compressor is energy that isn't being used to turn the wheels, representing a mechanical inefficiency inherent in the design. There are several types of superchargers, including roots, twin screw, and centrifugal, each with slightly different efficiency and compression characteristics. For example, a roots-type supercharger, famously seen sticking out of the bonnets of classic American muscle cars, moves air in discrete pockets. A centrifugal supercharger, on the other hand, functions more like the compressor side of a turbocharger, with its boost building exponentially with revolutions. Despite these variations, the core principle remains the same, using the engine's crankshaft power to compress intake air, delivering immediate boost at the cost of some efficiency. A great example is the Dodge Challenger Hellcat, which uses a supercharger to achieve its monstrous power figures. A turbocharger, often simply called a turbo, also compresses air to force into the engine. However, its power source is far more ingenious. Instead of being driven by a belt connected to the crankshaft, a turbocharger is powered by the hot, high-pressure exhaust gases that are expelled from the engine after combustion. These gases, which would otherwise be wasted energy sent out of the tailpipe, are channeled to spin a turbine wheel. This turbine is connected via a shaft to another wheel, called the compressor, which is located on the engine's intake side. As the exhaust gases spin the turbine, the compressor spins as well, sucking in and compressing fresh air for the engine. This clever recycling of waste energy is the turbocharger's greatest strength. It does not create the same parasitic loss as a supercharger because it isn't mechanically draining power from the crankshaft. This makes turbocharging a more efficient way to add power to an engine. By using energy that would otherwise be lost, a turbocharged engine can produce significant power gains, while potentially maintaining or even improving fuel economy compared to a larger, naturally aspirated engine of similar output. This efficiency is why turbochargers have become so popular in modern cars, from high-performance sports cars to economical family hatchbacks. The main disadvantage of a turbocharger is a phenomenon known as turbo lag. Because the turbo relies on exhaust gases to spin up, there is a delay between when you press the accelerator and when the turbo provides maximum boost. At low engine speeds, there isn't enough exhaust gas flow to spin the turbine quickly. As you accelerate, the exhaust flow increases, the turbine spins faster, and the boost begins to build. This delay can result in a non-linear power delivery, where the car feels sluggish for a moment before a sudden surge of power arrives. Modern engineering has greatly reduced turbo lag with innovations like twin-scroll turbos and variable geometry turbines, but it remains an inherent characteristic. Managing the boost pressure is critical in a turbocharged system to prevent the turbo from spinning too fast and creating excessive pressure that could damage the engine. A component called a wastegate is used. The wastegate is a valve that can divert some of the exhaust gas around the turbine wheel, effectively controlling its speed and the amount of boost it produces. Similarly, a blow-off valve, or diverter valve, is used to release excess pressure from the intake side when the throttle is closed, preventing damage to the compressor. A well-known example of a turbocharged car is the Porsche 911 Turbo, a model that has built its entire legacy around this technology. When comparing superchargers and turbochargers, the best choice really depends on the driver's priorities. For those who crave instant throttle response and a linear power band, the supercharger is often the preferred option. It is ideal for applications like drag racing, where immediate power off the line is crucial. The satisfying, instantaneous shove in the back that a supercharged engine provides feels very natural and controllable, mimicking the feel of a much larger engine. Cars like the Ford Mustang, Shelby GT 500, and the Jaguar F-Type R use superchargers to deliver this kind of raw, immediate, and visceral performance experience without any perceptible delay. On the other hand, for drivers who prioritize overall efficiency and high revolutions power, the turbocharger is the superior choice. Its ability to generate free power from waste exhaust gas makes it a more intelligent solution from an engineering standpoint, leading to better fuel economy. Turbochargers truly shine at medium to high engine speeds, where exhaust flow is strong, providing a thrilling surge of power that many enthusiasts find addictive. This makes them well suited for road racing and high-speed driving. The vast majority of modern performance cars, from the Volkswagen Golf GTI to the McLaren 720S, rely on turbochargers for their balance of immense power and relative efficiency. The drawbacks of each system have been mitigated over time. Superchargers have become more efficient, and modern engine management can minimize their impact on fuel consumption during gentle driving. Meanwhile, turbocharger technology has advanced dramatically to combat lag. Twin-turbo setups, where two smaller turbos are used instead of one large one, can spin up much faster. Variable geometry and twin-scroll designs also help to provide boost more quickly across a wider revolutions range, making modern turbocharged cars feel much more responsive than their predecessors from a decade or two ago. This has blurred the lines between the two, but the fundamental characteristics remain. In summary, the choice is between instant, belt-driven power versus efficient, exhaust-driven power. A supercharger offers immediate lag-free response at the cost of some mechanical efficiency. A turbocharger offers superior efficiency and impressive top-end power by recycling waste energy, but with the potential for a slight delay in power delivery. Both are fantastic ways to supercharge your driving experience, but they deliver that excitement in distinctly different ways. The supercharger gives you a powerful linear shove from the get-go, while the turbocharger provides a thrilling, efficient rush as the revs climb.